So you got to be able to graph either an exponential or logarithmic function. That's what these first two questions address. The second bullet point there, solve logarithmic and exponential equations with any base. And then our favorite, solving story problems. So that's what we're going to cover in Chapter 5. The next, let's go back to the logarithms here. So starting with the basic function, use transformations as needed to answer the following questions. Okay, 1 plus log base 2 of x plus 4. All right, identify the y-intercept. State the equation. Okay, there's a lot to do here. How do we find the y-intercept? Let x equal 0. Okay, so if this x, we get x plus, so 0 plus 4 is 4, log base 2 of 4. I better write this down. So if I plug in a 0 right here, that's going to be 1 plus log base 2 of 4. Exactly. Log base 2 of 4. 4, remember, is 2 squared. So we would write that as 1 plus log base 2 of 2 squared. The log base 2 cancels the base 2. So it's just 1 plus 2, which is 3. So the y-intercept is the point 0, 3. Any questions on that? Okay, the thing to remember about exponential and logarithmic graphs, they do have asymptotes. So the graphs that we just finished in Unit 2 had both horizontal and vertical. Logarithms and exponentials have one or the other. So the thing to remember about logarithms is they have a vertical asymptote, and exponentials have a horizontal asymptote. So what's the purpose of a vertical asymptote? Domain restriction. Okay. What can't you do with logarithms? What can't you put inside of a logarithm, I guess I'm asking? Negatives. So, or you can't evaluate a logarithm with negative values. You can plug negative values in for x as long as it doesn't make the whole expression inside negative. So could I plug in negative 3? Is that okay? Negative 3 plus 4 is positive, so that's fine. If it was just log base 2 of x, then the vertical asymptote's at 0. So this actually goes back to Chapter 2. This plus 4, we would agree, is inside the function, yes? So what kind of transformation is that if it's inside the function? Is it horizontal or vertical? Yeah, that's what we need to remember. It's horizontal. If it's inside the function, it's horizontal. So the plus 4 moves it to the left 4 units. So your vertical asymptote is going to be x equals negative 4. That's to the left 4 units. So your vertical asymptote is there, x equals negative 4. But just to recap, if there were no plus 4 and it was just log base 2 of x, where would that vertical asymptote be? That's 0. If it was x minus 4, then obviously it would move to the right 4 units. There is no horizontal asymptote, just a vertical one with logarithms. All right, find the domain and range. Did I skip one? Are we going to graph this at any time soon? That's the last step. Okay. Well, the purpose of the vertical asymptote is to help you determine the domain. The domain is going to be to the right of your vertical asymptote. And it doesn't include any values on the vertical asymptote, obviously. So it's not going to include 4. It's going to originate from 4 and go to infinity. So the domain is parenthesis negative 4. I think I said 4. I apologize. It's negative 4 to infinity. The vertical asymptote puts a restriction on the domain. There is not a restriction on the range for logarithms. So the range is all real numbers.
You have to write a negative infinity, or could you put ARE or ARN?
I'd accept that. Well, actually, it is specific. It says interval notation. So the math department would not accept it. So they wanted interval notation. Now we're just sketching the graph. Okay. Well, we already know where one point is. It's right here. The shape of logarithm graphs, if you remember, looks like this. It comes from negative infinity and passes through these points and kind of not levels off. It does increase, but not as quickly. We need a couple other points on the graph. So let's plug in some good values for x, meaning because we have log base 2, we're going to want to be careful what goes inside of here. For example, what if I plug in a 4? Why would a 4 for x be particularly good?
Because that's 2 to the third.
Because we get 8, which is 2 to the third. 8 can be written as 2 to the third. So the log base 2 would cancel the base of 2, leaving a 3. So it'd be 3 plus 1, which is 4. You following? So when I plugged in a 4 for x, 4 plus 4 is 8. Log base 2 of 8 is 3. 3 plus 1 is 4. So 4 comma 4 is on the graph. What would be another particularly wise value for x? Where are you?
-2.
-2 would be good. Yeah, why -2?
Because you get 2 and then that would just be 1 plus 1.
Log base 2 of 2. This actually came up as one of the bonus questions on this last exam, by the way. Now that you mention it, what is the log base 2 of 2? It's 1. There were a few students that crossed out everything and assumed it was 0, but there is still a 1 left over as an exponent. So the log base 2 of 2 is equal to 1. So if you plug in a 2 for x, or a -2 rather, you get the log base 2 of 2, which is 1. And then 1 plus 1 is 2. So -2 comma 2 is on the graph. 3 points is what has been required. So you need to show 3 points on that graph. Questions on logarithms? Graph logarithms, I mean. All right. That was from section 5.3, by the way. Graphing logarithms is in section 5.3. If you want to look at some other examples or look at your homework problems, 5.3. Graphing exponential is from 5.1. If you want to look at more problems for this, 5.1, graphing exponential functions. It's very similar because logarithms and exponentials are related to each other. So this -1 is not part of the exponential function. The exponential function is here, so the -1 is outside of it. Why is that so important to determine where the transformation is? If it's outside the function, it moves it up or down. In this case, you're right, it moves down 1. And remember, exponential functions have a horizontal asymptote. Logarithm functions have a vertical. So this one, if the horizontal asymptote is moved, it's going to be moved down 1 unit. So there's your horizontal. Well, that's actually part of, well, we're doing part B first. The horizontal asymptote is the line y equals -1. That's part B. Sorry, I went out of order there. Let's do part A. Find the y-intercept. Well, we let x equal 0, so 0 plus 2 is 2. 2 squared is 4. 4 minus 1 is 3. So another or y-intercept of 3. Where do you answer part B? Find the asymptote. It didn't explicitly state it's a horizontal asymptote. That's going to be up to you to remember that exponential functions have a horizontal asymptote. Logarithm functions have a vertical asymptote. For some reason, it took off the domain and range on this one. What would the domain be for exponential functions?
Negative infinity to positive infinity.
The domain is all real numbers, negative infinity. It's the range that's affected. The graph is going to be above this horizontal asymptote, so the range would be parenthesis -1 to infinity. For some reason, I didn't put that on there, but something to be prepared for. Anytime you graph something, you ought to be prepared to answer that question, domain and range. Now, part C, sketch the graph. We need a couple other points, so let's plug in x equals 1. That's kind of an easy one. X equals 1. So if we plug in a 1 for x, 1 plus 2 is 3. 2 cubed is 8. 8 minus 1 is 7. So 1 comma 7 is on the graph. I'm going to plug in -1. -1 plus 2 is 1. 2 to the first power is 2. 2 minus 1 is 1. So -1 comma 1 is on the graph. So the exponential function looks something like that. Questions on graphing exponential functions? Again, section 5.1 if you want to look at some other examples there.
Question.
Yeah.
Can you just go over again real quick how you got the asymptote?
Yeah.
If there isn't like a numerator and denominator, did you just plug in the 0 or?
So normally the horizontal asymptote would be at 0, but this -1 moved it down 1.
Okay.
If there was a +2, it would move it up 2. So it's the transformation that occurs outside the function. Yep. Okie dokie, let's do 3. Solving exponential equation, or logarithmic equations. This comes from section 5.4. If you're wanting more examples, section 5.4. This showed up as a bonus question on unit 3. Actually, no, it probably would have shown up on unit 4. The pitfall that students fall into is this. Most students remember what it is that cancels a logarithm. What cancels a logarithm? A base. But you cannot use multiple bases on the same side. So you can't cancel this logarithm and that logarithm by using 2 bases of 6 like that. That doesn't work. You can only use one single base on the left side and one single base on the right side. That's it. So you can't do it like that. But it is true that bases cancel logarithms, but what do you do if there's more than one logarithm? You have to combine them. Condensing logarithms. That's from section 5. It's actually 5.4, condensing logarithms. So solving logarithmic equations is 5.5, not 5.4. So we got to combine those into one logarithmic expression. That's called the product property, if you remember. There's a plus sign between them, which means you combine them using multiplication. If there was a minus sign there, you would combine them using division. Does this sound familiar? So that's the product and the quotient property. Because of the plus sign, you're going to multiply those 2 expressions. So you're going to multiply x plus 2 with x minus 3. So we combine it into one logarithmic expression like that. And again, if it had been a minus sign, then these would not be multiplying, these 2 would be dividing. Okay, that's all in section 5.4, combining logarithms. Now that we have a single logarithm, you are able to cancel it using a base of 6 here and a base of 6 there. The base of 6 cancels that one single logarithm. So what you're left with now is no longer a logarithmic equation, it's a quadratic equation. X plus 2 times x minus 3 is equal to 6. And I say quadratic, it may not look in the form of that's normally quadratic. Quadratic would be x squared, so you're going to have to multiply that left side first, because the way to solve a quadratic equation, remember, is to get one side equal to 0, but there's nothing to subtract 6 from over here. So you're going to want to multiply these 2 together, subtract the 6, and then hopefully it refactors into 2 different factors. So if we multiply those 2 together, you're going to get x squared minus x minus 6 equals 6. Now you can subtract the 6. So it's going to be x squared minus x minus 12 equals 0. Which does factor x minus 4 and x plus 3. And then he set each of those equal to 0. Now there is something else to remember here. This is kind of a mean trick. Remember what it is that you cannot do with logarithms? I mentioned this a few minutes ago. You can't use logarithms on a negative number. Now that doesn't necessarily mean that your solutions can't be negative. It just can't stay negative once you plug it in for x. For example, here x will equal negative 3, right? Negative 3 plus 2 is negative 1. That's no good. You can't take the log base 6 of negative 1. As with here, negative 3 minus 3 is negative 6. So is x equals negative 3 actually a solution? No. It's called extraneous. It's one of those words that I mentioned in Unit 3. But that doesn't imply that this one is good automatically because this one doesn't work. You still need to check it. If x equals 4 from this factor, 4 plus 2 is 6. That's fine. 4 minus 3 is 1. That's fine. So x equals 4. Thumbs up, right? X equals 4 would be the only valid solution here. X equals 4, x equals negative 3. What you would probably want to do is show that you crossed out x equals negative 3 because it's extraneous. And only circle x equals 4. All right. targets. So yikes. Oh, fun. We haven't done one like this in a long time. We've mostly dealt with compounded continuously. Oh, boy. So if it had said compounded continuously, which of the two formulas would you use? The PERT? Okay, but it says compounded quarterly. And that's an important thing to not overlook. If it's compounded quarterly, you have to use this function here. And if it's compounded quarterly, that means n equals 4. Quarterly means 4 times a year.
Is that how it would be written on the test, where it would give you both
Yes.
equations?
You're not going to have to remember what these formulas are. You do have to remember which one to use in which situation.
Okay.
So n equals 4 quarterly. If the interest rate is 7%, this is another common mistake I'll see. R equals not 7. R equals 0.07, yeah. So remember that you change that percent into an actual number, which is 0.07. And then $8,000 is your value for P. $16,000 is the value for A. That's the future amount. So what is it exactly that we're solving for then? How long will it take as a value of time? Yep. Solve for T. So if we plug in all the known values, 16,000 goes in place of A, 8,000 goes in place of P, 1 plus 0.07 over 4 times 4, or to raise to a power of 4t. What kind of equation is this? And when I ask that, where is the variable that we're solving for? It's in the exponent, which makes this exponential. So in the back of your mind, you think, how do we solve an exponential equation? With logarithms. We have to use logarithms to solve an exponential equation. Just like with the last problem, number 3, we had to use exponentials to cancel the logarithm. Boy, let's get rid of that 8,000. What do you suggest we do with that 8,000? We would want to do divide because the 8,000 is multiplying, right? So let's divide that 8,000. That means we're going to get a 2 over here. The purpose of using logarithms is to cancel the base so that this is no longer an exponent. As long as our variable is an exponent, it's going to be hard to solve. So we got to figure out some way to make this not an exponent. Yeah, what if we combine this, into just a value? What is 1 plus 0.07 divided by 4? It's going to be 1.0 something.
1.0175.
Okay, so let's do say that again?
0.0175.
Thank you. So now at least it looks a little better. Let me ask you this. If this happened to be a 3, you see where my finger's pointing? If that happened to be a 3, what logarithm would you use? Log base 3, right? That's kind of a no-brainer. I showed you, though, that it actually doesn't matter what logarithm you use. And it is in your notes from section 5.5 if you go back and look. And here's why I'm bringing this up. The question that the answer they're going to want is something that we use a calculator for anyway. What are the only 2 logarithms that a calculator is going to do? Natural log or log base 10. You can use those 2 logarithms to solve any logarithmic equation if you remember exactly what it is you're doing. If I use a natural log, for example, here, is that going to cancel this base? No. So why use a natural log? Well, stay with me here on this one. If I use a natural log right there and a natural log right here, it is true that these 2 don't cancel out, but there is another property called the power property where it says if you have a logarithm with an exponent, where does that exponent go? If the bases don't cancel, where does that exponent go? Do you remember this? It goes in front of the logarithm. And if this exponent goes down in front of the logarithm as a coefficient, is it an exponent any longer? No. We can continue to solve it at that point. And why would we want to use natural log of all logarithms? It's on your calculator. It's an easy logarithm on your calculator. And you can also do the same thing with common log, log. The same thing applies. So you can take this exponent and move it down in front of that logarithm, and it is no longer an exponent. So what we would have now is natural log of 2 equals 4 times t times the natural log of 0.0175. Oh, sorry, 1, thank you. 1.0175. It's actually not much more to do to solve for t. We're solving for t, right? Well, it's being multiplied by 4 and the natural log of this. So if we want to isolate t, all we got to do is divide by 4 natural log of 1.0175. So if we divide by 4 natural log of 1.0175 on both sides, then that tells us the value of t. T is equal to, and this is where your calculator is going to help you, natural log of 2 divided by 4 times the natural log of that, which we'll have to approximate. All right, who's got my back here? I can't do that in my head. And I guess I do have a calculator, I guess. All right. Let's see, natural log, where are you? Natural log 2 divided by 4 times natural log 1.0175. I'm getting 9.988. I better get somebody to back me up on that.
Yep.
Okay, thank you. 9.988. Now, what is that? $9.998? 9.988? It's a matter of time, so it's got to be years.
If we manage to get it in the exact form for the calculator, is that...
That would
I
be...
feel like I botch the calculator sometimes, so...
I would accept that.
No, okay.
Yeah, and the reason I would accept it, there are still some professors in this department that don't allow students to use calculators of any kinds, so you have to use it. You have to leave it in that form.
Sorry.
That's mean.
I know. So, yeah, I'd accept it in that form.
Okay.
So obviously, in this case, we can use context to determine that 9.988 is in years. But for instance, when we plug in for n, we put 4 because it's 4 times a year. So how could we know that that's not 9.988 times a year?
Wait, let me.
Not in there.
Well, that was a fun one. I really enjoyed that. Who's with me? No? Yeah, okay, one person? Good.
Honestly, having the formula makes it like less horrible.
Yeah.
When we were taking the test, I didn't know we were going to be given the formulas, and I was like panicking. I was going to have to remember
Yeah.
like all of that. So
Just to wrap up, though, if this had said continuously, you do per, right? Okay. All right, number 5. Cost sometime to 2,000, where C of t is measured in thousands. Estimate the average cost of a house in the year 2010. Estimate the average. So what is it that C of t represents? It's a function of time. So what does C represent?
Cost.
The cost. So estimate the average cost. What they're asking us to do is plug in something for t so that we can find C. We want to find the average cost. But it says estimate the average cost of a house in 2010. So we've got to figure out exactly how this has been defined. And it says it's the average cost of a house t years after the year 2000. So 2010 is 10 years after the year 2000. So what the value of t am I plugging in? 10. So really part A is just a plug and chug. You plug in a 10, run it through the formula, see what you get for C. So that's not really anything to solve. So if you plug in C of 10 for t equals 10, you're going to get 100 plus 25 e to the 0.03 times 10. Like I said, that's just strictly work on your calculator now. So 100 plus 25. Oh boy. So I'm getting 133 0.746 for C. Well, we do need to clarify. We do need to clarify this because there's a little clarifier at the very end of the description where C of T, do you see what I'm saying here? Is measured in thousands of dollars. So it's not saying that the cost is 133. It's 133,000. You following that? So you could. What would be the best way to represent this? 0.75 thousand. You'd have to write the word thousand, or you could simply say 133,750 or 0.75, right? No, 750 like that. Or you could write it like that. But anyway, you'd have to indicate that you know that this answer doesn't represent $133. It's $133,000. Make sense? Okay, what about part B then? According to the model, when
Finding T and plugging that, 250 for CC, right?
Yep. When will the average cost? That means we're solving for a value of time. When in some town the average cost was $250,000. So again, using this descriptor that C of T is measured in thousands of dollars, we're not going to put this value in for C. 250,000 would mean that C equals 250. So you plug in a 250 for C. And then solve for T. Well, again, T is an exponent. Is that good or bad? Yeah, we don't want to solve it if it's an exponent. So eventually we're going to have to use a logarithm to cancel the base E. And this is nice because what cancels the base E? Natural log. But we want to get rid of that 25 first, and we got to get rid of this 100. So let's do this in one step. If I subtract 100, get 150. If you divide by 25, 150 divided by 25 is 6. Yep. So this turns into 6 equals e to the 0.03 t. Now we can use natural log. And I want to make sure it's clear, this one's going to be a little different than the last one. So going back to question 5, I still used natural log here, even though we didn't have a base e. These two did not cancel out. You see where my finger's pointing? This natural log didn't cancel that base. What did happen is the 4t dropped down in front. But here, natural log is the opposite of a base e, so those are going to cancel out. Yes? That's something to remember. Natural log and base e cancel out. So the 0.03t is just by itself. It's no longer an exponent. So what we have is natural log of 6 equals 0.03t. We can now divide by 0.03. So t equals natural log of 6 divided by 0.03. You can leave it in exact form like that if you want, or you can use a calculator. And I'm getting 59.7. 0.73.
So that's saying just under 60 years past 2000, right?
Yes.
Okay.
So it's a subtle play on words, but it's not saying how long will it take. It's saying when will it reach. So actually our answer should be a year, a calendar year. Does that make sense? The question is actually when will the average cost of a house sometimes reach? So you have to explain this. You could either say it's 59 years past the year 2000 or the year 2059 and August of the year 2059 or whatever 0.73 is of a year. Okay? So the actual answer to part B would be the year 2059. Or you could simply say 59 years past 2000. Okay, we're almost done with unit, well, not unit 3, we're almost done with chapter 5 of unit 3. Write the single logarithm here. Going to kind of speed this up so we can get done before we have to leave. All of these coefficients in front of the logarithms, where did they come from? Yeah, those were exponents at one point. So those move up. So log base 2 of a to the third plus log base 2 of b to the 1/2 minus log base 2 of c squared. So you move those back up as exponents. And then you condense moving from left to right. If you condense these two first, that makes a product. Yep, that's the product property. So log base 2 of a cubed b to the 1/2 minus log base 2 of c squared. Then if you combine those, since there's a minus sign between them, those are going to divide. Now, most students do remember that it's division. Tell me what I did wrong here. I'm going to purposely write this incorrect. And I've shown you this before, but I want to make sure you remember. Because I'm still dividing, right? What did I do wrong? You should only have one logarithm. It says combine into a single logarithm, right? So it's not just that you're using division. You've got to write this as a single logarithm. It's not that the logarithms are dividing. It's the expression inside of it that divides. So this would be incorrect. You condense it into a single logarithm, and then you divide the terms inside of it. So it would be a cubed b to the 1/2 in the numerator, and then c squared is in the denominator. That's much different than having two separate logarithms dividing. Okay? And then the next one is just the opposite of what we... Is that actually the same problem? Close to it. That's kind of... Well, so you separate first the... If we want to separate the fraction, we're going to use a minus. So log base 4 of the numerator minus log base 4 of the denominator. So you first separate the quotient part of that using a subtract. And then we have to split up the product. By product, I mean right here. What separates the product when using the product rule? Addition, yeah. So now we're going to separate this into two more logarithms using addition. So log base 4 of a squared plus log base 4 b cubed minus log base 4 of c to the 4th. And finally, you move the coefficient to the front so you have no more exponents. And that would be the final result there.
What are the differences in the instructions again? Like, how do you, like, I guess like when you look at it, you know, you're gonna like undo it, and some of them you're going to like combine it. So
This one says write the following as a single logarithm, so that implies we're putting it all back together into one. This one says write as the sum or difference. Sum or difference means plus or minus, so you're adding or subtracting several logarithms at that point. That's what the directions there mean. Now, chapter 8, when we get to it here, these are the sequences and series, if you remember this from a couple weeks ago, finding patterns in those lists of numbers. Does that sound familiar? So that's part of unit 3, which was chapter 8. I'm happy to stay for however long it takes to finish this one, so we at least finish the video. I know we'll go past time. If you need to leave, that's fine, but I need to get this done anyway, so I'll probably just stay and talk to an empty room if no one's here. Chapter 8. Arithmetic sequence was from, 8.2 if you want to look at more examples, but specifically arithmetic sequences was 8.2. If it hadn't specified this as arithmetic, what indication is there just based on this that it is arithmetic? And that's important to recognize what kind of sequence it is.
It's adding two A's.
It's adding the same thing every time. Yep. If it had been multiplying the same thing every time, that'd be geometric. So if they hadn't included that descriptor, then you need to be able to find out what the sequence is. And it's arithmetic because it's adding 4 every time. Okay, good. Find the expression for the nth term. Now, I was going to show you. You will have a formula sheet on the final exam that gives all the formulas for Unit 8, or for Chapter 8, rather. And one of them on there is this one. This is the nth term of an arithmetic sequence. So it would really just be up to you to know what the different things are. So a sub 1 obviously is the first term. D is the common difference. So in this sequence, the common difference is 4. And the first term is 3. And you don't plug anything in, at least for this, how we're using this formula, you don't plug anything in for n. So you would just need to plug in the first term and the common difference of 4. So it would be, for part A sub n equals 3 plus n minus 1 times 4. And you simplify the formula there. So 4 times n is 4n. 4 times negative 1 is negative 4. But negative 4 plus 3 is negative 1. So you would write that as 4n minus 1. And I showed you kind of a quicker way of doing that, if you remember when we went over this in class from 8.2. If it's arithmetic, then your nth term formula is going to be linear. Linear meaning y equals mx plus b. M is kind of like your slope or the common difference, and that's a common difference of 4. This negative 1 is usually where your y-intercept is. What's the x value of a y-intercept? 0. If there were a 0 term in front of the first term, what would that 0 term be? Negative 1. So that's why there's that negative. So that was the kind of a shortcut way I explained in class. But if you want to use the formula, that's fine. Just got to make sure you simplify it and write it in that. Okay. Now part B, find the 100th term. Now that we have the nth term, that should be pretty easy. To find the 100th term, you just plug in 100 for n. So that's 400 minus 1. So a sub 100 is 399. Now part C uses a different formula. Find the sum of the first 100 terms. So also on that formula sheet, you're going to find what's called the partial sum of an arithmetic sequence. And it is partial sum because we're only adding 100 terms. We're not adding an infinite number of terms. We're only adding 100 terms. So the partial sum of an arithmetic sequence is n over 2, and then you add the first term to the last term that you're adding. So that would be the formula you would see, or the formula that you would need to use. So it's not a matter of remembering the formula, it's a matter of knowing what all the pieces mean. N, in this case, represents how many terms you're adding. So we're adding the first 100 terms, so obviously n is 100. First term would be the first term in the sequence, so that's 3. A sub n means the last term of the portion that you're adding. So we're adding the first 100 terms. So what is the 100th term? Well, we answered that in part B. So it would be 100 over 2 times 3 plus 399. So that's 50 times 402, just 20,100.
And with them giving us the equations, they're not going to be labeled, right? They're just going to be given to us?
So again, for questions like these, it's not a matter of remembering their formula, it's knowing how to use it. These formulas aren't labeled on the formula sheet, so you do need to know what this formula is. So you got to go back into chapter 8 and look at your notes and be able to recognize them. Question 2, a theater has 21 first 15. So this is going to be 15 plus 17 plus, and each of the remaining rows has 2 more seats than the so that'd be plus 19 plus 21 plus, and there's 20 rows. How many seats are there in the theater? I guess if you wanted to, you could just figure out what all 20 values are going to be. So this would be 23, 25, 27, and then you can just make sure there's 20 numbers and then add them together. But what if the theater had 400 rows of seats? That would be a little bit more of a task. What kind of sequence is this? 15, 17, 19, 21? It's arithmetic. So the way that's intended to do this is to figure out what the formula is. So the formula is 2n, because it's a common difference of 2. And if you wanted to use this formula here, you could plug in the first value of 15, run it through, but it's going to be 2n plus 13. That's the nth term, 2n plus 13. And really what we're doing is finding a partial sum. It's this formula that we really need to use. How many terms are we adding together? 20. So n would be 20. The first term is 15. What is the last term? What's the term at the 20th row? Well, if we plug in a 20 here,
53.
yeah, it's going to be 20 times 2 is 40. 40 plus 13 is 50. So in the 20th row, there's 53 seats. So that's the value that would go here. So I'm going to write that a sub 20 equals 53. So now we could use the sum formula. The sum is 20 divided by 2. The first row has 15 seats. The 20th row rather has 53 seats. So we're just using the partial sum formula for an arithmetic series. So that's,
10 times 60.
let's see,
680.
15, yeah. What are we using a calculator for? 680. It's kind of a small theater. That would also be from section 8.2. Now question 3, a geometric sequence, those are from 8.3. Find the expression for the nth term. So again, the formula will be on a formula sheet, but it's not going to explicitly say this is the formula for the nth term of a geometric sequence. You're just going to have to be able to recognize it. What you'll see is something that looks like this, a sub 1, and then we have the common ratio, and we have n minus 1 as the exponent. That's the nth term of a geometric sequence. So what would you need to be able to recognize in this is what is the first term and what is the common ratio. Now the first term is easy to recognize. It's just whatever's written first. Common ratio, you've got to be careful. How do you go from 1 to 1/2? And remember, we're multiplying. So what is it that you're multiplying by to go from here to here to here and to there? And it's negative 1/2. So the common ratio is negative 1/2, and the first term is 1. So it would be a sub n equals 1 times negative 1/2 to a power of n minus 1.
If you couldn't see it super easily, like what it's multiplied by, you would just divide, you would just like
You would-
divide the second term by the first.
Exactly.
Okay. Like,
Or the third term by the second term. Knowing that it's geometric means that you can just take any two terms and divide the one previous to the one, and that'll give you the common ratio. Find the sixth term. Honestly, we already have the first four terms, so it might just be easier to complete the pattern. But if you didn't want to complete the pattern because it was like they're asking for the 15th term, you would just plug into the formula, right? So if we plugged in a 6, for example, 6 minus 1 is 5. 1/2 to the 5th power is negative 1/32. Negative 1/32 times 1 is negative 1/32. But if we wanted to continue the pattern here, negative 1/8 times negative 1/2 is 1/16, and then 1/16 times negative 1/2 is negative 1/32. So you get the same thing. Either way, for part B, the sixth term is negative 1/32.
Sorry if I interrupted you.
No, go, keep going.
Whenever you are multiplying that exponent, would it be best to, I don't know, I don't know if it's me, probably not my calculator. I get so confused as like what order to do, especially when it comes to like exponents. But we would just do like,
So if you're going to plug something like this into your calculator,
yeah.
so depending on what kind of calculator you have, I would do your base to the exponent first and then multiply at the end. Is that, and then if the base is a fraction, you could put it as a decimal, or you could put the fraction in parentheses and then raise it to the exponent. That might be where your calculator, if it's a fraction, you're going to want to put it in a parenthesis and then raise it.
Where I mess up so much is where when I'm trying to like put a fraction in the calculator,
Yeah.
and then like multiply it by something else, I'm like, anyway.
Some calculators are easier to do decimals instead of a fraction.
Probably just better for my brain, but it's really decimal.
So for part C, the sum of the first 10 terms, now this is going to be a different sum formula than this one. This is the sum of an arithmetic sequence. There's another sum formula on the formula sheet that's going to be first term, and then you have 1 minus r to the n, like that. So that's going to be the sum of the geometric series. So you're going to have to know what all of those mean. The first term obviously is the first term 1. R is the common ratio. N is the number of terms that are being added. So if it wants the first 10 terms, then R would be 10. Or sorry, N would be 10. R is negative 1/2. So this one just says, set up the problem, do not simplify. What is it saying? Do not simplify. Just, oh, okay. So what they're saying is just put the things in where they would go. You don't need to really simplify it. Just use a calculator at that point. So plug in the values into the formula and then use a calculator, essentially, if I understand it right, is what they're saying. So it would be 1 for the first term, and then 1 minus, I'm going to go ahead and use decimals here, negative 0.5 to the 10th power, divided by 1 minus negative 0.5. And then, from there, they say don't worry about simplifying that expression. Just use a calculator to figure out what everything is. Mm-hmm. .666.
Now we're cursed.
I know. Dang thing. See you Monday. All right. Find the infinite sum. That's another formula. It's the first term divided by 1 minus r. And the thing to remember here, this only works if r is less, if the common ratio is less than 1. So you got to figure out first what the common ratio is. Because it says if the sum doesn't exist, you need to state that it doesn't exist. So how do you go from 1 to 1/5 to 1/25? What's the common ratio here? Times it by 1/5. So r equals 1/5, which is less than 1. So what that means is this formula will work to find the infinite sum. So it's just a matter of plugging in the values. The first term is 1, and the common ratio is 1/5. 1 minus 1/5 is 4/5. 1 divided by 4/5 is 5/4. Now, if the common ratio had been greater than 1, you would have just said the infinite sum does not exist.
Can you say that again?
So if r is greater than 1, or less than negative 1, so it could be like negative 10, or... So the common ratio has to be a value that's less than 1, or the absolute value has to be less than 1. So it could be like negative 1/2 or negative 1/5, but it just, if it's bigger than 1 or less than negative 1, yeah, then the sum does not exist. Oh, I was hoping we'd get one like this. I actually wasn't. That's sarcastic. These take forever. Use the binomial theorem or Pascal's triangle to expand the binomial. Okay, well, let's see what Pascal's triangle does. If we're raising it to the 5th power, remember we need 6 rows of Pascal's triangle. So there's 5 rows. Here's the 6th row. So this row is going to tell us what the coefficients are of each term. 1, 5, 10, 10, 5, 1.
So do you do one more row than the exponent?
Yes. Yep. You always do one more row than the exponent. So if we're raising to the 5th power, we need the 6th row. So these are our coefficients. We just now need to know what the terms are. So the first term is going to be this coefficient, 1, and then it's going to be this term, 2x raised to that power. Now, if you remember, I talked about this when we did Unit 3 exam. There's a huge difference in writing 2x to the 5th like that, or quantity 2x to the 5th power. The whole term needs to be raised to the 5th power, so it does have to be in a parenthesis like that, and then your coefficient is 1. Now, 1 times that isn't going to change it, so you don't really need the 1. What is important here is that the 2x is in a parenthesis raised to the 5th power. That's your first term. Now the next term is going to have 5 as a coefficient. And this time 2x is raised to the 4th power. And we need to include now the other term, 1, is raised to the first power. So just going back to some of the things we talked about in section 8.6, every term has exponents that add to the original exponent here. So if you look at this whole term, we have an exponent of 4 and an exponent of 1. 4 plus 1 is 5. So every time you create a term, you need to make sure that the sum of these two exponents is equal to whatever you start with. For example, the next term is going to have 10 as a coefficient. And then 2x is going to be raised to the third power. And then 1 is going to be raised to the second power. Again, the sum of these two exponents always has to be 5 in every term. And we have another 10 as a coefficient. Again, we're just getting these from the bottom row here of this Pascal's triangle. And for this term, 2x is raised to the second power and 1 is raised to the third power.
So how do you know which one gets which exponent? Like the 2 or the third?
So if you think about this is kind of like A and B. If you look back at your notes from section 8.6, anytime we expanded a binomial, we always started with that first term A. And in this case, if it's raised to the fifth power, it's going to be A to the fifth. And then the next term is going to be A to the fourth, and then B to the first. And then it's A to the third and B squared. It always follows that pattern where the term that's in the front of this, or at the beginning of this binomial, always starts with the highest exponent. And then it decreases by 1. But then the other term in that binomial, 1, starts with the lower exponent and increases by 1 every time. So the A value is going to decrease and the B value is going to increase every time you make a new term, if that answers your question.
Yeah.
Okay, the next term is going to be 5 as a coefficient. And now 2x is raised to the first power. And 1 is raised to the fourth power. And finally, the last term is going to have 1 as a coefficient. And then, I mean, technically you could say that 2x still has to have an exponent, but what would be the exponent of 2x now? 0. And anything with an exponent of 0 means it's 1. So 2x to the 0 power is 1. So the 2x really isn't there. It's just this 1 here that has an exponent of 5. So it's 1 to the fifth power is your last term. So we just need to simplify here. And I say just, you've got to be careful. And that's where these parentheses are so important, because if you don't have the parenthesis around this term, for example, you would just call it 2x to the fifth. But it's not. It's 2x quantity raised to the fifth power, which is 2x times 2x times 2x. So it actually ends up being 32x to the fifth. And then here we have the product 2x raised to the fourth power. So that's 16x to the fourth. But then that 16 is multiplied by 5. And 16 times 5 is 90. So that's 90. X to the fourth. Now, we're kind of fortunate that this last term in the binomial was 1. If this had been something like 2, then you would, assuming that you have something on your exam that's not a 1, simply a 1 right here. So let's say you had a 2. It would be 2x to the fourth, which is 16x to the fourth. 16 times 5 is 90. And then you would multiply 90 by whatever value that is. Okay. Here we have 2x cubed, so that makes 2x raised to the third power is 8x cubed. And then 8 times 10 is 80. And then 1 squared is still 1. So that's 80 x to the third. 2x raised to the second power is 4x squared. 4 times 10 is 40. 40 times 1 is 40. So that's 40 x squared. Here, 2x to the first power is 2x. 2x times 10. 5 is 10. 10 times 1 is still 10, so that's 10x, and then 1 to the 5th power is 1. So that is the expansion of 2x plus 1 raised to the 5th power.
I know we're trying to hurry, but actually didn't learn this super well when we learned it in class.
So the binomial theorem is n factorial divided by r factorial n minus r factorial. That's the it's called the binomial theorem. And the reason it may make more sense to use the binomial theorem to answer question 6 is it's not asking for the entire expansion. They're asking for what's the coefficient of the term that would have b to the 4th in it, if that makes sense. So if you think about expanding all of these terms, every single term is going to have a to a certain power and b to a certain power, right? I guess except for the first term. What's the first term going to be? A to the 6th. So I guess technically there is still a b there, but it's b to the 0. And then the next term is going to have something a to the 5th, b to the 1st. And then the next term is going to have a to the 4th, b squared. Is this making sense? And then the next term is going to be a cubed, b to the 3rd. And then finally the term somewhere in there is going to have some kind of a b to the 4th with an a squared in it. So the question is, what's the coefficient of that term? I guess we could find it from Pascal's triangle, because it's only to the 6th power, which means we would need one more row here. So if we added one more row, it would be 1, 6, 15, 20, 15, 6, and 1. Those would be all of the coefficients for every term. We just need now to pick out the exact coefficient that would contain b to the 4th. So the first term would be something a to the 6th, b to the 0. This term would be a to the 5th, b to the 1st. This is a to the 4th, b squared. This one here is a to the 3rd, b to the 3rd. This one here is a to the squared, b to the 4th. But you got to kind of be careful there, because this is the coefficient just here. We also have all of these other values that affect the coefficient. Does that make sense? So you could use Pascal's triangle.
Would you multiply it by like a?
So it would be that one particular term that uses this is 15, and then it's a squared, and then it's 3b raised to the 4th power, right? So then you could take 3 to the 4th power, which is 81, and then you could take 81 and multiply it by 15, and that's going to give you the coefficient of that entire term. So it would be 81 times 15, which is 1,215. So the coefficient of the term that contains b to the 4th is 1,215. I know. Now, again, we were fortunate that they only wanted b to the 4th, and it was raised to the 6th power, so it wasn't that much more difficult to write the 7th row of Pascal's triangle. If it had said, what's the coefficient of the term, and it's raised to the 50th power, then...
The professor wants to grade that. So
I know.
Put it on the test. So
But that's where the binomial theorem could come in handy. N is the original exponent, so n would be 6. R is, in this case, would be 4, because we want the b to the 4th. So if we did 6 factorial divided by 4 factorial, and then 6 minus 4 would be 2, so that's 2 factorial. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, and then 4 factorial is 4 times 3 times 2 times 1, and then 2 factorial is another 2 times 1. The nice thing about how this formula works is the 4 times 3 times 2 times 1 cancel out, So you have 6 times 5, which is 30, and 30 divided by 2 is 15. So we still get the same value, 15, using that binomial theorem. All that told us was what the original coefficient of the term is before it's simplified.
How did you find what's in the parentheses, the n minus r? I know it's an r, but when you're looking at just what 6 is giving you, the a plus 3b is 6.
So n is the original exponent. In this case, r, I chose to be 4 because it's b to the 4th.
So what are the exclamation points for?
That's called factorial. It's a mathematical operation that you probably haven't seen before. We talked about it in section 8.6. Factorial means you take this number and multiply it by every whole number beneath it. So 6 times 5 times 4 times 3 times 2 times 1.
Okay.
That's all that operation means.
So what's on the numerator, the n in the numerator is going to be the same as the n in the parentheses in the denominator?
Yeah.
Okay. One just has a fancy tail.
Yeah.
Okay.
All right. I think that's it for